Good morning and welcome everyone. This is Manish Nath from Hex Universe and I am going to be your host for today's session. Firstly, I want to thank everyone for taking their time to join us today. Now, before moving on towards our main event, let me give you a brief introduction about Hex Universe. So Hex Universe is a space education and research-based platform which helps students to pursue their career in the field of space science and technology. We are on the mission of building the biggest community of space science and technology. Also, we help students to work on projects related to space science. Coming back to our today's webinar, this session is organized in collaboration with SS Citizen Science Group, Akashganga Science Media, and Craftsview Center. And our topic for today is R&D at Home India Citizen Science for Black Hole Galaxy Coevolution Studies. And today we have none other than Dr. Ananda Hota with us. He is an UGC faculty at UM-DAE Center for Excellence in Basic Sciences and also a principal investigator at R&D Home Astronomy Laboratory. We are all really glad to have him here with us today. So without any further ado, I'd like to request Dr. Ananda to proceed with today's session. Thank you, everyone, and this is all from my side.
Thank you for inviting me. Can you hear me?
Yes, sir, we can hear you.
Okay, great. See, I often start my talk in a unconventional way. I am very informal in my approach. Students and teacher relationship improves when they discuss a lot. Not only one delivers and other listens. Even one step ahead is a research. Research guide and student almost become friends so that they can argue and all thoughts can be corrected. So I would prefer that whenever you don't understand something, you note it down and feel free to discuss those things. Remembering something from the textbook or from some YouTube talk doesn't develop your understanding much. It is when you start processing them, start chewing those thoughts, and start cross-correlating them, then only you develop your understanding. As simple as the following thing that I will tell you. That if you have bulb in your room, you see your shadows very clearly. But if you have a tube light in your room, you don't see sharp shadow. As simple as this fact, we don't question these things. In the morning time, you don't see your shadow. Why? So my point basically is you have to keep processing various information that you learn or listen from various sources, books, talks, etc. When you all process them, cross-correlate them, you develop good questions. So listen to me talk and feel free to discuss at the end in length. Only then the slides that I have created, they are used properly. Otherwise, many things are quoted from different paper. You can get into internet and listen so many talks. For example, Finman lecture is there in the internet, free. How many of you are reading? How many of you are complaining that there is no good textbook, no good teacher in your college? Plenty. But the Finman, one of the best physics teacher, his lectures, his book is freely available for everybody to learn physics. Okay, let's go. I will start sharing my slide and we will discuss slide by slide from there. I have many slides. Let's see how much we can properly describe and understand. If necessary, I will use my graphics tablet and draw something and explain. Let's start with the slides. Somebody confirm if you can listen, see my slides properly.
Yes, sir.
Yes.
Great. See, as the title says, it is a science topic plus a description of a socio-scientific experiment that is read at home. Why do you need to learn something like this? Because the information or education or research or outreach landscape actually has changed. It is no longer in that hierarchical way that you listen from various radio, TV, etc., outreach level, popularization of science level. Then you go for a formal education on a particular course. You finish the education, then you go for research on that particular topic. It is one after the other. Research and outreach, information from any source is now short-circuited. It's now connected. It has become a circle. It is not a triangle anymore. So today, what we're learning can also make certain contribution to research. When a PhD student writes a research paper, he may be giving 90% contribution to a research paper. 10, 20 author papers, somebody may be contributing 9%. But citizen science, even if it is a 0.9%, 1%, this is genuine contribution to research and you are credited. So that phase has come because of the internet and computer and the data overflow that actually all the systems, instruments have created. So time has come that whatever be your career status, your college, your university may or may not be knowing there is a citizen science research happening everywhere. Students already know and students should without fail participate. Don't miss the flight. Okay, so that is why Red at Home Citizen Science I will connect with you. And the topic that we focus on in Red at Home, real astronomy discovery sitting at home anywhere in India, is black hole galaxy coevolution, especially using radio data from our own nation's pride giant meteor radio telescope and any wavelength telescope that is available, because I'm kind of a multi-wavelength extragalactic person. That is what my publication research expertise. As you can see here, I'm a UGC faculty UM-DAE CEBS. I launched Red at Home in 2013. I'm a member of various academic institutions, International Astronomical Union, Square Kilometer Area India Consortium, Astronomical Society of India, Principal Scientific Advisors Consultative Group, etc. These are basically gives that how many different fonts I am involved. Not only I'm teaching in one institute or doing in one institute, but there are many other aspects of every academic that you have in the country. Okay, so giving a perspective, Indian science. Independence till today, if you think, those time it was Raman, Bhabha, Saha, etc., etc., individual excellences. Then we thought of, we want milk, we want rice, we want wheat for the people to feed properly. So science got focused on self-reliance. Then a phase came when technology was denied to us. So we had to develop everything on our own, space, atomic, all kind of research. Then a phase came, turmeric, neem, haldi, etc. that we have to fight that these things we knew. Western world cannot claim that we are rediscovering it and we have patent on it. So we have to fight on that. Today we know, because of the globalized economy, that we all have to be competitive enough so that we innovate and convert those innovations to economic growth, so that we feed our people properly for a better life, we make our country safe, and at the same time, from that benefit, we give a positive feedback to the fundamental research that can be technology later on. So launching satellite, there was argument that it will help fisheries, it will help agriculture, it will help people, it will help weather prediction, etc. But going to Mars, there is no benefit to common man. No, there is indirect benefit. So that is why fundamental science and applied science, countries' growth strategy, all are interconnected. Stick to science no longer is correct. So from there, basically in a single line, one can define that what we all need is a scalable model of education and research, which will be faster, sustainable, and inclusive growth of the nation. How we can do? Let's come back to our own education. What do we think? We are all fascinated by the first image of the black hole, Event Horizon Telescope, etc. Big things, Higgs boson, etc., etc. We are all fascinated. We want to work on that topic. Yes, absolutely important. But what do we have? Our astronomy facility. Maybe we have a small telescope at home or in the school. That's it. This cannot contribute to research in black hole this way. So these are educational tools, almost toys for astronomy. They are not research facilities. So how do you do that? How do you be part of this kind of big research, breakthrough research? So our science education may be at the college, university level, but the time has come that through citizen science, you have to do research sitting at home. Your facilities cannot limit your growth. You be part of a bigger facility by connecting through citizen science. That is what is Radiothon is designed for. I am providing you, basically, we are providing you training, data from the largest radio telescope, GMRT. Then at home, whatever astronomy passion you have, you can still contribute to some research result while you are still learning what is basics of astronomy. This is has to be the purpose, that you may be aiming a big, but you have a small facility. So be part of a collaboratory, large scale collaboratory, so that you can be connected to big research. So what are the big research facilities we have then? This 1-inch, 4-inch, 10-inch telescope cannot give you much breakthrough result. So these are our research facilities actually in India in astronomy. What is that? You all know this diameter radio telescope. This is 3.6 meter Devastal optical telescope near Nainital. This is from NCERT TFR. This is from Aries Institute in Nainital. So these are actually largest optical telescope we have in India. Largest radio telescope not only in India but actually of this kind in the whole world. It's 3 times bigger than the American-based BLA telescope, radio telescope. Which are this? These are actually, you can see a Tata Sumo here. 45-meter diameter long dish antennas. They all can track 30 of them spread over 25 kilometers. Here to here is actually, you can make a 50-meter run almost. Right? So this is a plot of all the optical telescopes in the world when they were started functioning. 1950, 1970, 1980, 2010, 2022, we are now. Big telescope means what is the mirror size of this telescope? 4 meter, 8 meter, 12 meter. Now we are part of 30-meter telescope. So currently we have a 3.6 meter telescope, less than the 4 meter below poverty line. Right? So we are slowly catching up. We are far behind in radio, but we are much ahead in radio. That was optically we may be lagging. That is why we are part of TMT. But radio-wise, we are very good. The size of these circles that you see are the size of the collecting area, size of the radio telescopes. So you can see GMRT is here. VLA is here, American one. LOFAR is coming, slightly different technology, different parameter space. So this way, this antenna wise, we are largest. So whatever we can see actually is going to be most sensitive or the best in the world if we apply our best with our own telescope. That's the reason scientists from all over the world come and use GMRT. Along with we Indians, there are 30, 40 different countries who come to India and use GMRT. So let's move forward. So using GMRT, it's my own work. So maybe I'm a bit biased, but probably this was the discovery of a spiral host episodic radio galaxy, was first international news-making discovery from GMRT. Press release by NRO USA, Royal Society, NCRT-FR, of course. So you can see in this picture, optical picture is in yellow. Blue picture is from VLA America, USA, and the red picture from GMRT India. So three different telescopes data have been combined to interpret how the black hole at the center is affecting by the plasma outflow to the galaxy. We will talk about this thing later on. That is why it is important to make use of your best facilities so that you can surprise or you can contribute, you can shine in the whole world and make your country proud. Unless you are part of that kind of big success, you will not be counted much. Like unless you demonstrate your power in the Olympic race, nobody is going to listen to you. If you win gold medal in the Olympic, it starts affecting very nice things in your stock exchange also. Okay, everything is interconnected. So because of the discovery, the father of Indian radio astronomy, Govind Swarup, appreciated our effort. This discovery that was press released by NSF USA. Govind Swarup NCRT-FR, who is not part of the team, described the finding as an outstanding discovery that is very important for cluster formation model. Cluster means clusters of galaxies, not star, and highlights the importance of sensitive observations at meter wavelength provided by the GMRT. This is 1 meter wavelength radio wave in which we have imaged that, roughly 300 megahertz, 1 meter wavelength size. So from there, I got the idea that how to involve many people and train them so that GMRT makes many more discoveries. Whole sky is full of radio sources. GMRT has already produced survey. What we need to train people. That is where this idea is actually perfectly fine for India, perfectly best for India. What we are good at, we are best in one aspect that no other country is. Largest pool of science and technology manpower, largest pool of IT companies and engineers, largest number of mobile phone, computers connected to internet, all communicating in English. So that the moment anything happens in the world, we all can start learning immediately. There's no delay of translation or anything. So if we apply this aspect of our global competitive edge to this aspect with the largest radio telescope we have, we can do wonderful things. That's the origin of radiometrics. When I launched in 2013, simply Facebook group, no infrastructure, no money, nothing. But the idea was so good that with time, 24 institutes started supporting and hosting our training camps. What we do training, we select people based on their Facebook activity, but we host them in a research institute for 7 days. Free food, free stay, everything they get free. The institutes are giving free. Why? They know that it is good for the students, it is good for the country. It is best use of the telescope's power that we have. Not only Indian, but this approach is so unique and so successful. This is not only first Indian citizen science in astronomy in 2013, but it started getting appreciated from international organizations and getting selected for their presentations there. Recently, in SOIU meeting, citizen science leaders from NASA, from Universe, everybody was presenting along with our results there. But it's so proud moment, but at the same time, we have a long way to go. So what do you do actually? And quickly, I will summarize in one slide that you just need to remember. What is it? It is that we have a small resource as a website. We have a small resource as a Facebook group where we discuss and learn from each other. We have been busy in conducting discovery camps in various research institutes to get you trained. From that training workshop, from that group discussion activity, with the use of the tool, we now grow some preliminary discovery reports that goes to GMRT research proposal. From there, we can publish. So the professional astronomers publish from the GMRT data, but the preliminary discovery report that the members have created, it has contributed directly. So those direct contributors can become co-author in the research paper. This is how a hierarchy has been created, what we call flying pyramid. Anybody who learns galaxy, radio observation, understanding can be selected to the training camp. This is a Facebook group, 4,700 members. This is the website, which has a radio data analysis tool there, simple tool. And this is a photograph of a group discussion and training that goes for 7 days. All of you can be part of it. That's why there are 4,700 members. They all believe that we can be part of it one day. If we are good enough, if we are competitive enough, we demonstrate, they will be selected. Just a simple picture. This is ICTS program certificate. ICTS means International Center for Theoretical Sciences of the Tata Institute of Fundamental Research in Bangalore. The group was stationed there for 7 days. Another one-day exposure, ISR Berhampur actually, MPSC Rajasthan online program. You can be part of one-day exposure. One-day exposure, from there people are selected to 7-day training program. 7-day training program is designed for making preliminary discoveries. And then you become kind of, if you discover something important, you get co-authorship. So government, various institutes are now well aware that how to involve public, how to give an exposure to the public that what big science instrument investment the country is making. We need to tell people so that tomorrow's students who are first time listening in this public talk, like you today, day after you can become actually the person who will be using that big facility. This is our flying pyramid model. That I'm there, single person maybe, but 30 institutes are supporting institutes. 30 scientists are contributing to the training program and discoveries. They are here being co-author also. 165 people who are trained for 1 week. Thousands are learning online Rgb image analysis. That's what thousands of active learner in Facebook in a group of this. So another science media that I have, S3 and 3 India, 13,000 people are connected. So people can contribute small discoveries, and that becomes a big research paper with the help of training program helping institutes, with the help of supporting scientists who will help us in make publications and discovery. So this is what is a statistics, 1 year statistics of our Facebook group. Soon after this process description so that you can be directly benefited, I will go to science part. It's a 1 year statistics. You can see how many posts have been made, how many comments made, how many active members, reactions, like, love, etc., etc. Over 1 year time, April 2021 to April 2022. What do you see? There are nearly 2,000 active members from this nearly 5,000 member group. 15 RGB image or comments on Galaxies they are posting per day on average. What does it mean? This like spikes that you see are our weekly live classes. There they discuss nothing else, no star party discussion, nothing, no NASA news discussion. It's precisely on what galaxy image, what wavelength, what feature, what structure, what evolutionary aspect, what physics aspect of the galaxy image you can understand. No other discussion there. That's how this is actually a science discussion and and the quantitative way of telling how much active we are in directly discussing and learning science. If anybody posts something else, that person will be removed. It's a very strict purpose scientific research group. So what do you get ultimately? Ultimately, nearly 50 out of those 1 week trained, they are doing MS or PhD abroad. In India also, there are many of them doing. They are spread all over India. This is what is your ultimate career growth, contributed by participation in astrophysics. Because what you discover, what you become co-author in a paper, what you even become co-investigator in GMRT proposal, that goes to your recommendation letter that I will be writing. That go to your CV that you can describe. So participation in citizen science in any topic that you love is a very strong reflection of that you are actually committed beyond your course of studies, beyond your certain certificate that you get. And then the people who, suppose you are participating in astronomy citizen science and applying for a PhD or MS in astronomy, they will certainly take interest in your CV because you stand out from the rest. Everybody would have got MSc or BSc or whatever mark they have. You have to stand out. Only then you have an edge over others. So, as I was telling, you can be part of, you may be at the bottom, but it's sure you can grow and be part of a research proposal, part of a paper, irrespective of which college you belong to, as long as you have internet and you participate through Facebook or through Google Meet. Okay, so that's why Father of Indian Radio Astronomy appreciates us, writes letter, encourages. Recently he passed away, we lost him, but at the same time, what he led, the creation of GMRT, is a legacy that we have to make best use of it. This is dedicated to the nation, dedicated to science. I will go quickly. A lot of research, ISR Berhampur, ISR Kolkata, they all appreciate because they see a different kind of educating and involving undergraduate students in research is coming up. That is right at home. They felicitate me. Odisha government, the Sam Chandrasekhar Award, that's all I give. Sam Chandrasekhar is a famous traditional astronomer. And this is what you know, recognition from different institutes. Now let's come to the science. What science we do? What are we focused on? These are socio-scientific experiments, as I said. What are we actually focused on? Exactly करते क्या हैं हम लोग? क्या discussion करते हैं galaxy के बारे में? That particular point will be starting now. So the primary science goal of Red at Home is galaxy black hole co-evolution. This has been described in 2 papers. Read the paper title on the right hand side. New results on exotic galaxy speca and discovering many more specas with Red at Home network. Another paper, there is 2014 when we launched in 2013. The conference paper. This is journal paper 2016. Tracking galaxy evolution through low frequency radio continuum observations using SCA and citizen science research using multi-wavelength data. You can see the speca discovery I just described is another NASA news of our work. What is that? It has a radio galaxy that GMRT sees typically, that is radio galaxy, star formation in the galaxy. How the black holes plasma outflow is affecting the star formation in the host galaxy. We spotted a very interesting and caught in the act kind of galaxy. That made a lot of news, lakhs of Google hits. This topic is actually so important that the Square Kilometre Array, the largest radio telescope that countries are building, that has hosted some kind of 1, 2, 3, 4, 5, 6, 7, 8 science goal of this new radio telescope. One of them, the galaxy star formation black hole activity evolution, is this galaxy that my NASA news of 2012. What does it mean? It reflects that this is an important topic. It's a cutting edge research. We don't understand how black hole and star formation in galaxies are going hand in hand. Why that is happening? So we are focusing on that particular aspect. No other aspect. For example, why there is a spiral arm, why there is a bar. The kind of dynamical aspect we are not talking. We are not talking about theoretical aspect. We are talking about what in galaxy evolution GMRT can contribute and other data we can add in to make a progress in the direction that people are thinking one of the 8 important goals of the big radio telescope. Okay, that's why square kilometer array, that website, international organization, that will be 10 times bigger than the GMRT actually. So they have given website release for the people to know. So this is basically our science aspect that we can research. As I told, to start with your understanding, we have a simple tool in our website. Go to the website, redactomindia.org. On the header itself, you can find the Rgb Maker Tool. When you click redactomindia.org/Rgb Maker, you need to have just put your name so that the image belongs to you, you understand. Then you put the galaxy name, NGC82, M82, whatever you wish. You to start with your understanding. Then you can leave the default image size or make it small, make it big. That's it. There will be many multi-wavelength images will be displayed in your screen. Your training starts from there. Because it is a simple, uniform tool for everybody, the moment you post, the structure and color, culture is same, protocol is same. So everybody immediately understand what data you have combined and what does it mean. In a particular picture, if it is looking red, what does it mean? If it is looking blue, what does it mean? Okay, so the moment you start making an RGB image, you can be part of this activity called Daily Galaxy RGBC. Depending on what is the date, month name, suppose this is, what is the day? Today is 9th April. So today you will be discussing NGC 0409, NGC 409. Tomorrow 410. So every day the different target is defined for you, so that you keep on discussing every day. Little bit of post a comment, post a question. Why this galaxy is looking red? Why this galaxy has a tidal tail-like feature? Is it interacting? Is it related or not related? Anything you comes to your mind. Keep on commenting every day, night, every weekend, whenever you wish. And slowly you grow over the time. There is no load. There is no overburden. There is no exam here. Similarly, when there is an activity, a camp or a workshop, this is today, this is a 1 hour session only. Suppose we had organized for 1 full day. There you would have been doing this, that nationwide inter-university galaxy RGBC analysis. Different part, students are in different part. They will be, according to their pin code of their location, they will be analyzing different galaxies. So we will look at each other's images, discuss what is difference, and we start learning from each other's analysis. This is how actually we grow in our experience as fast as possible in a specific direction: red, green, blue, radio contour image analysis of galaxies. Okay, so this is just for the picture of describing what we do. We use infrared, optical, UV, RGB images from WISE telescope, NASA's optical telescope DSS survey, Galaxy NASA's telescope. Then we have read ROR images, TGSS, GMRT is our own GMRT's radio image, optical image, and VLA USS radio image. 20 centimeter image, 2 meter wavelength image, infrared image, ultraviolet image. So we have basically 1, 2, 3, 4, 5 wavelength data combined for galaxies and displayed. हमारे सामने परोस दिया गया है. But it is presented in front of you in a uniform way. You start interpreting, discussing, so that you understand each other's language. You start learning the jargons of using it. For example, what is a point source? What is a compact source? What is a diffuse emission? What is a compact emission? What are extended sources? What are point sources? Is this a star or a galaxy? Many things from the same uniform minimum knowledge of these 5 images you will start analyzing. Okay. So, any questions so far? If anybody wants to ask. We'll go to basics of astronomy part soon. Anybody? Shobhan. Okay. No questions so far. It's no problem. We will be starting 5 minutes.
If anybody have any question, please ask your questions to sir right now, because later you may not get a chance to ask.
Yes. The question is here. I can also answer. Somebody asked me. It's a bachelor's degree program. Yes. What we used to say is any BSc, BE, BTech can do research using geometry data. So ABCD research kind of thing. So if you are a BSc first year onwards, you have passed BSc, MSc, any degree from any university, you all can be part of it. You need to be a valid member from a university education system or a passed out from any university. If you are an Indian student from any university, you can join. Okay, good. 50 number of people are watching it, but at the end, hopefully, there will be more discussions. Anka Kamble, your microphone has a problem. Why don't you type your question if you had something? It's getting echoes. Okay, let's go back. You quickly start. The moment you say astronomy, you start looking at constellations. This is how easy thing everybody can do. That's why we started with that. So there are bright stars, there are faint stars, etc., etc. One can develop understanding of that. Here comes the first color picture from a famous astrophotographer, Ajay Talwar. This is our Indian astronomical observatory in Hanle, Ladakh. What do you see in the stellar trail? Different stars are of different brightness and different color. Why they are of different color? The simple answer is this. With displacement law, you can think of the stars kind of a steady state, long thermal object, long-lived object, and they are like black bodies. So lambda max t equal to constant or whatever we already know, that suppose an object is looking, a thermally heated object looking red, or its peak is in longer wavelength, it is actually a cooler object. And the object is looking blue, or in shorter wavelength maximum light is coming from, that object is a hotter object. So blue hot is hotter than red hot. Okay. Other thing this plot is showing is that blue objects emit more light in total than red objects in the same temperature. Okay. So all these blue looking objects are actually hotter stars. You may or may not be knowing, today this is the Chaitra month, Hindu calendar, Chaitra month, summer season. Chaitra month name comes from the star named Chitra. Chitra in English is called Spica. Spica is a very blue looking bright star which is 11 times more massive than our sun. Its surface temperature is 26,000 degrees. That is why the temperature is high, and that is why the maximum light comes in blue band. Maximum light from our sun comes around yellow-green region. It is less surface temperature. How much is it? Not 26,000, but 5,000, 6,000 around. So now you know the things which are looking blue are actually hot, massive stars. They produce a lot of heat. They consume a lot of fuel, like a Honda Activa versus a Enfield Bullet. They consume more. They are more powerful. So they finish their fuel faster and they die out in supernova early. So these massive blue O and B type stars explode in few millions of years, whereas our sun is living for 4.5 billion years. So here your understanding of color, brightness, and the age starts. So temperature, age, all these things are connected. Let me say, starting to go back later on. So this is what is a picture. The blue picture is from ultraviolet image. Red picture is from an infrared image, 22 micron. In the green picture from optical image. So in this galaxy, The ultraviolet bright regions are on the end of the spiral arcs. UV is not coming much from the center. These are the stars bluer than the optically blue, means ultraviolet. So they are much hotter, 25,000, 30,000 temperature kind of thing. So they are hot, massive O and V type stars who will die out soon are here. Sun-like, long-lived, several billions of year stars are actually here. And what is there in 22 micron? The temperature will be around 300 Kelvin, 200 Kelvin. So they cannot be star. They are cold gas, cold pH, polycyclic aromatic hydrocarbon, or dust-like thing. Okay, so in a single picture of UV optical IR, we are getting multiple components of the space. For example, here, IR 22 micron is in red, optical is in green. What do you see? This is a shock wave of the interstellar gas that is there, dust that is there. The star is moving, a stellar wind, like solar wind. It's pushing aside all this material. It is seen. Similarly here, these are plates or kritika. You see the stars, fine, but in infrared, the IOU image we have created, you see the dust cloud, which is cold. This is 200 degree Kelvin. The stars are 6,000 degree Kelvin. We'll come back to this point later on. That is small white contours you see. That is from GMRT. GMRT telescope, being largest in the world in radio, cannot see these bright stars that any naked eye can see, because the radiation mechanism is different. That's very important in radio astronomy. That's why I am giving you hint now, that one can see far away galaxies, active black holes creating plasma jets, but cannot see the nearest stars for Kritika constellation. Okay, let's move on. That is the multi-wavelength image. Now I'm quickly going to spectroscopy. What is in spectroscopy? That when you take a spectrum with a prism or a grating, you get many lines: emission line, absorption line. What do you extract? The beautiful thing is that the stars, people used to think stars are holes in the iron sphere and cosmic fire is seen through it. That is a Greek time. They were the brilliant scientists in those days. They would speculate this much, not more than that. Today we know it is made up of like hydrogen bombs. Hydrogen is being converted to helium. So through spectroscopy, we come to know this important thing, that heaven is made up of same stuff as Earth. So the same physics laws apply. From there we figure out that various emission lines from electrons orbit jump, we can interpret what is the state of matter there, what is the velocity there, etc., etc. Here comes. A particular spectrum will have a fixed wavelength. Because of the Doppler thing, you can see them H alpha, H beta, H gamma, H delta. If you bring this star emitting H alpha line so fast towards us, it can be blue shifted and it will be seen here. If it is going away from us, it will be even further red and go to infrared. So using this simple Doppler effect, we can estimate the kinematics and content of the galaxies both, and then the expansion of the universe ultimately. We'll come to that. See, for example, here is a picture of a optical galaxy, face on spiral galaxy, beautiful. And the right hand side is the atomic hydrogen gas emission from this galaxy. See how the gas is much farther, which come back towards the gravitational attraction towards the center, and they starts forming molecular gas cloud that starts forming stars. What is this atomic hydrogen? Atomic hydrogen is simply proton at the center, electron going around. They all have angular momentum number quantized, so you can think of that they are rotating classically. It's an analogy only. If proton and electron both are parallelly rotating or spinning parallel, they have a higher energy state. They want to come down to the lower energy state, there is anti-parallel spin. So in this tiny energy difference del E, that is h nu, del E equal to h nu, that nu or the frequency of that transition comes around 1400 megahertz or roughly wavelength 20 centimeters. So that spectral line is seen in radio. If you see them, So if I look at a galaxy is 6164, for example, here, then you will see the 21 centimeter line emission coming here. There is noise here, there is noise here. This is GMRT spectrum of this atomic hydrogen. All the atomic hydrogen in that galaxy, for example, this galaxy, is giving a spectral line, all that is seen here. What is seen as a 21 centimeter line? Why it is there's a width? Because half of the galaxy is blue shifted, half of the galaxy's gas is red shifted. That is seen, can be seen here. This is H alpha emission from the spiral galaxy, H1 emission from the spiral galaxy. When you convert that where the line is seen, you can see that the half of the gas of the galaxy is red shifted, half of the gas of the galaxy is blue shifted, because the galaxy is rotating. It is going away from you, it is coming towards you. So this is what it gives a kinematic understanding of the rotating system that is galaxy. There is an individual galaxy. Now we'll go to collective galaxies. You all know this picture, Hubble Deep Field. What is there in this picture? That there are different kind of galaxies, spiral, bar, non-spiral, elliptical, etc. What is interesting that you hardly realize is that they are of different kind, but are also seen from different redshift. I described you that whatever spectral line you see, because of the motion, you will be red shifted or blue shifted. You already have heard from various talks that the universe is expanding. So all these galaxies that you see in this picture, some of them are receding or going away from us at faster speed, some are at less faster speed. So their light is also getting blue shifted or red shifted. So all the light is also getting red shifted or blue shifted from the galaxy. If a galaxy is like sun, made up of sun-like stars, say for example here, all the wavelength, maximum light should be coming in green, yellow wavelength range. Because of redshift, everything can be shifted to red. Even if more redshift is given or is moving at faster velocity, it can cross the red and become infrared. This is what is plotted in this picture. That redshift 0 galaxy, nearby galaxy, if it is seen in optical band UG, R, I, Z, it is a nearby universe. If it is seen at longer wavelength, it is actually from far away universe. Even farther, longer, farther universe. So it is possible that the wavelength can be, the light can be seen at infrared. That is why we are sending James Webb Space Telescope. That because of redshift, the optical emission from those galaxies cannot be seen in optical wavelength in our Hubble Space Telescope. If the objects are too far, the objects are moving away at faster speed, objects are early universe galaxies. So you need to put an infrared telescope to understand how those early galaxies behave in optical band. You need to observe them in infrared so that you understand how those early universe galaxies look like in optical band. Because of universe is expanding, everything is red shifted. Okay. So from this picture, we are going to sort out matter now. Different kind of galaxy we put in different boxes. To put that, the nearby universe galaxies are either spiral or elliptical. Going a little backward in time, closer to Big Bang. When did the Big Bang happen? Big Bang happened 13 billion years ago, 13.6, roughly 14. Okay. So what we see farther away, light has actually taken billions of years to reach us. We are here. So roughly you can say how many years after the Big Bang the galaxy is seen. So today the universe is 14 billion years, nearby galaxies you see. How the galaxies are, which are the galaxies 9 billion years after the Big Bang, which are the galaxies 5 billion years after the Big Bang that is seen, which are the galaxies 2 billion years after the Big Bang we are seeing. Now sort them in different boxes. Nearby galaxies, this box, bit farther away, too far away. What do you see? That we are unable to see this standard spiral structure or elliptical structure in them. Today it's a kind of bimodal, that all are plant or animal, all are spiral or elliptical. But long time back, neither they were clearly spiral nor they were clearly elliptical. So they were in a formative era of their life. How did these clumpy galaxies have evolved to become elliptical or spiral? That is what is galaxy evolution. If you go 1 billion years back, there was no dinosaur, no human. Go to 2 billion years back, there was only single cell in creature. Probably plant or animal, they were not defined. Similarly, this like biological evolution, galaxies have also been evolving from early universe to today. And what are the physical processes that govern their evolution? Make them look different today, behave them differently today. That is galaxy evolution study. Similar to galaxies, black hole may be also changing, and they are probably co-evolving. That is what is the purpose of our understanding. So let me check the time. 47. So I need to shape something else. This particular thing I will probably show. Okay. So when you observe galaxies in multiple wavelengths, you measure in ultraviolet, you measure in infrared, you measure in optical. And you plot how bright they are in different wavelengths. Then a synthetic spectrum from theory and observation combined can be created. So if a galaxy's brightness in UV, optical, IR falls like this, so that it is a red curve, it must be a very old galaxy, like our sun, several billions of years old. If the galaxy's ultraviolet brightness is here, infrared is here, it falls to the lavender color curve or violet color curve, the galaxy stars will be few million years old. This is how we age date the stars in the galaxy. Now I will jump too much and go to understanding something else. There is the stars of the galaxy. Their color can be giving us age of the stars. Now some galaxies, mostly elliptical, which has massive black hole, they create these plasma jets. That is seen only in radio band. This the pink thing is radio, not seen in anything else. And this plasma that is coming out from the galaxy's center, because of the matter falling into the black hole, one has to find out what is the age to understand how it has been evolving. To do that, I will have to go too far. Okay. The way the plasma behaves is, it is not like black body, it is different. How is it different? This spectrum is necessary to show. The spectrum, right hand plot, right hand picture is focused, brightness or intensity and frequency. If you plot in the black body behavior and the radio plasma behavior are different. Like Planck's law, it has a rise and a fall. This is thermal emission. But the non-thermal plasma from the jet that is created by the black hole accretion process, they behave with a straight line, the blue line, which has a lot of emission in low frequency and little emission in the high frequency. Thermally, it has a rise and a fall, but that is straight. So, the plasma that is come out from those galaxies will have a straight line behavior when there is fresh plasma coming out. For example, from this galaxy Speca, the plasma that has come out and forming this balloon-like structure, it has a straight power law behavior. They are plasma. But after a while, the black hole can stop accreting matter and plasma jet creation can stop. So like a smoker is smoking and stops smoking, the smoke will start spreading in all direction, in diffusing in all direction. So plasma can also diffuse in all direction, like become irregular and faint. So in the daytime, everybody looks for this kind of faint and fuzzy, irregular radio emission blobs. What happens to them? They no longer will have that straight line behavior. That is what is the case. Fresh plasma will have a straight line frequency brightness versus frequency power law behavior. When it becomes old, that the straight line has become curved because high frequency emission is coming from high energy particles. They radiate faster, so they lose energy faster. Once you see from low frequency and high frequency BLA and GMRT, both the images of a radio source, if it is still bright in the Indian data and almost missing in the American data, you can come to know that red looking stuff in your red, green, blue RGB image is actually old plasma. From there, where the frequency curvature is happening, like a T critical frequency, this is the equation. Time, you can figure out when the plasma has started diffusing or no energy supply from black hole is happening to the plasma blob, can be figured out by knowing the break frequency, where the emission spectrum is curving, bending, and the redshift of the source and the cosmic microwave background magnetic field. Let's not go to all those details. But what I'm saying is that looking at the old plasma, faint, fuzzy, bright in GMRT data, fainter in American data, we can spot the plasma that has come out of the black hole accretion process long back. That is how we spot emission in GMRT's data by citizen scientists and understand how the black hole activity, outflow activity history has been co-evolving with age of the stars in the galaxy. You have to age date the stars, age date the plasma. There is one theory called AGN feedback where they say the black hole has created this plasma which has removed the cold gas from the galaxy, and that is not allowing new stars to form in ellipticals. And that is why the elliptical galaxies, where is the elliptical galaxy and spiral galaxy example that you know, this is vital. Blue young stars are forming, elliptical, no blue young star. For billions of years, it is not forming any star. And this probably is the culprit that the radio outflow from the center has removed the gas and there is no cold gas to form new star. So we want to understand this important concept that through galaxy merger, how black hole and galaxies are co-evolving and why elliptical galaxies are not forming stars, possibly because the plasma outflow from the black hole has killed the star formation future of galaxies. So in the group, if you join, you will all learn this RGB image making and how do you interpret this thing. Spectra is seen in RGB images. Looking faint and red is the point to understand that this may be the case that we can find a smoking gun evidence of this black hole's feedback on galaxy in destroying the future star formation of a galaxy. If you join the group, slowly from RGB image analysis, we will learn, we will discover, we will publish and grow your career and make our country proud with many fundamental discoveries. That's related. Okay. Let me end my talk here. Thank you. Questions? I'll be happy to answer. Yes, if you have done a BSc Physics from any college, any university, then you are eligible to join the from Facebook group. You can do anything for your living, but you can enjoy doing astronomy learning, astronomy research. That is what a citizen science is. Okay?
Okay, sir, that question is actually mine. So,
Okay.
what I mean, I am in that group. and I have seen that every Saturday you conduct classes.
Yes.
So, uh, what is the step? What are the steps? I just need to join those classes, and I will get to know the further steps.
You simply start making RGB images, start discussing, and your comments and your discussion will demonstrate basically that you are understanding things and you are interested in it. From there, you will be selected based on your RGB image discussion and post. You will be selected to iAstronomer group. There it will be further. Then you will be trained on GMRT data. Once you spot something interesting, then it can go to GMRT paper and proposal. Then it will go to publications. This is how you grow. Okay. Okay, Cosmic Girl has asked, do we need any software for this imaging? No. The software that you need to have is not for imaging. RGB images are created by the web tool. You don't have to download anything. It is just your web browser. But when you are selected to discover something from GMRT data, then only one image display software called DS9 to display FITS file, because JPEG file doesn't give you quantitative information. You need to have astronomical data in FITS file format, flexible image transport format. Once you install DS9 in Windows, Linux, any system it works, then you are good to go. That is enough. So you create a preliminary report. There is no advanced software installation or trick that you need to learn. That is why it is citizen science. The things has to be simple so that large people can participate. Advanced level thing, the professional's job. They will carry forward the job. Your discovery, preliminary discovery reports. Anybody else? We were sending a request to join Reddit from Facebook group. There are a few criteria that you have to have. It is written there already. You need to express which university you have studied or you are studying in. You need to have a proper profile photo. Some authentic looking profile has to be there. Because there are 4,700 people, there are junk profiles who try to join there so that they can advertise something. And I will have to be wasting my time and deleting their post and removing them from the group. So some eligibility criteria, some strictness is there. Amit Raka, probably communicating. If we are from commerce, science, or arts field, but interested, so can we be part of it? As you mentioned, a graduate student. Can we even enroll school kids for some activity? See, everybody has limited resources, limited time in life. If there are plenty of people and some support we have, I am ready to pass it on, involve school children. Okay. Many things that suppose I describe, the signal to noise ratio has to be significantly above 3 sigma level. I can explain to some extent, but if there are problems, I cannot keep explaining everybody because of the limitations of our human hours. I put a minimum limit of BSc first year at least, so that they understand what I'm saying. So if there are people who are interested to give more training to non-science students, I'm happy to expand, but it doesn't happen quickly. So that is why the limitation is there. So currently we are simply accepting science undergraduate students and anybody qualified with science degree from anywhere. Hex-Star, we have some questions from YouTube chat. Is there any relation between fifth state of matter and black hole? Yeah, see, these are questions that you can ask to Google or anybody. There are plenty of answers. But what you should be asking in this discussion group, as I said, good question. So what is relevant here? So that my time and people who are listening to your question, they get some maximum benefit out of it. Okay, personally, outside this group, I can answer this fifth state of matter and black hole, but it doesn't really look relevant in the socio-scientific context and the learning of black hole and galaxy co-evolution. What is the state of matter in black hole? Doesn't really matter at the moment when we are discovering sources from the citizen science process. Second question, we know that black hole attracts even a photon, but how it emits radiation? This is a genuine confusion. This is why actually it deserves an explanation. Okay. You can see my screen. So, let me take. Yes, you can see my screen. See, for example, left hand picture. Okay. See, the Rgb Maker tool is asking you only galaxy name. Galaxy name is defined from the date, right? So the moment you put the date into NGC date, then the galaxy name is defined. Don't have to remember or look for anything. NGC 409, 410, another tomorrow.